Hey guys, sorry I can't be there today. I'm at ACT doing some stuff. And no, I don't have my iPhone suspended from fishing line from the ceiling, videotaping a piece of paper while I write. That would be ridiculous of a way to make a lesson plan. So anyways, today we're going to look into something that's, I think, pretty interesting. We're going to look into something called an indeterminate forms. And we've talked about this a lot, but I've kind of waxed over it a little bit. Indeterminate forms are things like this. Plus minus infinity, 0 over 0, 1 to the infinity, 0 to the 0, kind of crazy things like this that don't really make any sense algebraically. But with calculus and limits, we can actually sort of think about them. And you might be asking yourself right now, why would I even ever think about this? I don't really want to do that. And the answer is that you can get into a situation, especially with fractions, where the top or the bottom, the numerator or the denominator, will actually have a specific behavior that does result in an answer. But if you plug the limit directly in, like say something like this, like the limit as x goes to 0 of e to the x minus 1 all over sine x. If you plug 0 in right here, you're going to get e to the 0, which is 1. So you're going to get 1 minus 1 all over sine of 0, which is 0. So that becomes 0 over 0. So this is a situation that you might actually get yourself into, right? You have an exponential behavior and some sort of oscillating behavior, which is really common if you're thinking of something like the damped oscillation of car shocks and struts or anything like that. And this answer here is ridiculous. It's a non-answer. This is what we call an indeterminate form. And indeterminate means exactly what it sounds like. I'm not going to spell it right, sorry. This is an indeterminate form. Oh, you guys can't see that. I'm sorry. An indeterminate form means not that there's no answer, not that it's 0, not that it's infinity, but it means literally that you don't know. Like literally straight up, I don't know. So we have to do something to figure out what that's going to be. You know, is this 0? Does this spit out infinity? Because you could argue both ways, right? You could say, well, if the 0 on top is for real, then the whole thing is 0. If the 0 on the bottom is for real, then the whole thing goes to infinity, and, you know, like, deal with it, because, you know, something divided by 0 is infinity. Well, there's a subtle difference between 0 and infinity, or nothing and everything. So we kind of have to deal with that. So, oh man, it left little black marks. That's great. So let's do that problem that I was just dealing with right there. So the limit as x goes to 0 of e to the x minus 1 over sine x. Now, the real question here is which one of these wins? And that's really the big idea here when you're working with an indeterminate form. Again, these are the indeterminate forms that you should be thinking about, especially 0 over 0 and infinity over infinity. What does this do? Well, if the numerator wins, right, and it goes to 0, the whole thing goes to 0. If the denominator wins and gets to 0 first, then the whole thing goes to infinity. So it really is a question about how fast is the numerator versus the denominator. All right? So remember, if this one gets to 0 first, the whole thing goes to 0. If this one gets to 0 first, the whole thing goes to infinity. So the question there is, how fast are they? Which means we're talking about derivatives, which means we're not going to do a quotient rule to find the derivative of this whole thing. So no quotient rule. We're going to actually take the derivative of these separately and figure out how fast each individual piece is. So the derivative of the top, right, so we'll take d dx on the top, is something like e to the x, right? So if I derivative the top, or differentiate the top, I get e to the x minus 1, which is 0, so we get that on the top. And if I d dx this one, I get cosine x. Okay? So now let's look at how fast those are. Well, this one, if I plug in 0, right, this one's going to go to 1. And this one, if I plug in 0, this one is also going to go to 1. So it stands to reason that this thing actually ends up resulting in an answer of 1. So this becomes the limit as x goes to 0 of e to the x over cosine x, which equals 1, which is actually kind of an interesting result because we thought it was going to be something between 0 and infinity, which it in fact is between 0 and infinity, which I think is kind of cool. This has a special name. This is called L'Hopital's rule. And it's somewhere in chapter 7. I forget what section. I think it's like 7.2 or something like that. I'm sure Emily will find it. This is called L'Hopital's rule. And L'Hopital's rule is really awesome because it's talking about the rates of the denominator and the numerator. And if you write L'Hopital's rule in like sort of general form, like abstract mathy form, it looks like this. The limit as x goes to some number c of f of x over g of x equals the limit as x still goes to c of f prime of x over g prime of x if and only if, and I swear to God it's IFF with 2 F's, if and only if this is an indeterminate. Indeterminate of 0 over 0 or infinity over infinity. So this is really important. So this is true only if this spits out, right here. Let me turn that a little bit. If this fraction spits out 0 over 0 or infinity over infinity, and it could be plus or minus, it doesn't matter. So if that's true, that's a really janky arrow. I'm sorry, guys. Maybe I'll make it a little like it. It's a mushroom now. Okay, great. Fantastic. So if this guy becomes one of those, then this is true. Because, and here's the reason, because you're thinking about how fast they get there, right? If this one gets there first, then the result of the numerator is going to cause a different answer. If this one gets to the craziness first, then the denominator will cause the answer to be something very, very specific. Okay, I'm going to put up a second video that's another couple examples.